This lecture is about the processes in the core of the Sun. The learning goals are to be able to explain how and why proton-proton fusion that takes place in the core of the Sun, and that this was verified by neutrino measurements. The core is the innermost layer of the Sun. In 1939, Bethe proposed that the Sun contains in its core hydrogen nuclei moving at very high speeds. These nuclei undergo fusion to form nuclei of heavier elements, such as helium. In the process, a large amount of energy is liberated. It is the energy liberated during such nuclear reactions that we are receiving in the form of sunlight. Bethe was able to explain the birth of stars. Nuclear fusion occurs when two or more like-charged nuclei are forced together and combined to create a heavier and different nucleus. In the process, a great deal of energy is released. If the temperature of a gas is over 10 million Kelvin, the nuclei are moving fast enough to overcome the repulsive forces. A star becomes a main sequence star when the core temperature exceeds 10 million Kelvin. Figure 11.3 illustrates the concepts of nuclear fusion. The nucleus of an atom consists of two types of particles, protons and neutrons. Protons and neutrons have approximately the same mass. Protons have a positive electrical charge. Neutrons have no electrical charge. About 90% of the atoms in the Sun are hydrogen. In the core, which is hot, the protons move around at high speeds. Temperature is a measure of the average speed of motion. Like charges repel, so electrical forces would push the protons apart if they came close to one another. In order for nuclear fusion to take place, atom particles must get very close to one another, enough for one strong nuclear force to act. The strong nuclear force is a powerful but short-range force that holds atomic nuclei together. Due to the high temperatures and high densities in the core of the Sun, the protons can get close enough to fuse. When two protons fuse, they create a deuterium nucleus, plus a neutrino and a positron. A deuterium nucleus is one proton plus one neutron bonded together. A neutrino is a very light particle that does not interact well with other matter, and a positron is an anti-electron. It has the same mass as an electron, but the opposite charge, and when an electron and positron collide, they annihilate each other and release energy. The Sun emits a tremendous amount of energy each second. We also know the Sun has been shining for about 4.6 billion years. These two facts mean that the Sun must have an energy source to replace the energy that it is radiating into space. This energy source needs to be sustainable for a very long time. Ordinary chemical processes, such as burning, which is oxidation, are inadequate energy sources. The Sun's energy comes from the fusion of hydrogen nuclei into helium nuclei. This takes place in the central core of the Sun. The energy released by this process is sufficient to keep the Sun hot for about 10 billion years. The nuclear reactions in the Sun start with four hydrogen nuclei. Each is a single proton, and you end with one helium nucleus. This is called the proton-proton chain. The total mass of the original four protons is 1.007 times greater than the mass of the helium nucleus. In Einstein's theory of relativity, energy and mass are equivalent to one another. The relationship between them is given in the famous equation E equals mc squared. Here, E is a quantity of energy, m is an amount of mass, and speed is the speed of light. Because c is a very large number and c squared is an extremely large number, a small amount of mass is equivalent to a large amount of energy. The mass of the helium nucleus is smaller than that of the original hydrogen nuclei because binding energy is released during fusion. Binding energy is the amount of energy that must be supplied to pull things apart. It would take energy to pull the four particles in the helium nucleus apart because the nuclear forces that hold them together. For stars like the Sun, this is the primary method of nuclear fusion. The proton-proton chain can be conceptualized as a three-step process. Step 1. Two protons fuse to make a deuterium nucleus and also release a neutrino and positron. This step occurs twice for a single proton-proton chain reaction. Step 2. The deuterium nucleus and proton fuse to make helium-3. Helium-3 is a nucleus of two protons and one neutron. This also occurs twice for a single proton-proton chain reaction. Step 3. Two helium-3 nuclei fuse to form a helium-4 nucleus. and 2 unbonded protons. Helium-4 is a nucleus of 2 protons and 2 neutrons. Einstein showed that mass and energy are equivalent. There is a net loss of mass in the proton-proton fusion reaction, which is accounted for by the energy that is released. This process is often called hydrogen burning, even though it has nothing to do with chemical burning, which is oxidation. Nuclear fusion and burning are two very different things. All main sequence stars generate energy the same way, by hydrogen burning in their cores. Neutrinos are elementary particles of matter with no electrical charge and very little mass. Neutrinos are emitted in vast numbers by nuclear reactions that fuel the sun. Since the early 1970s, several experiments have detected neutrinos arriving on the Earth from the sun. Neutrinos are emitted directly from the core of the sun and escape interacting with virtually nothing. Being able to observe these neutrinos would give us a direct picture of what is happening in the core. Unfortunately, they are no more likely to interact with Earth-based detectors than they are with the sun. The only way to spot them is to have a huge detector volume and to be able to observe relatively rare, indirect, single interaction events. This is the highest energy neutrino ever observed. With an estimated energy of 1.14 peta-electrovolts, peta is the prefix meaning 10 to the 15, it was detected by the Ice Cube Neutrino Observatory at the South Pole on January 3, 2012. Ice Cube physicist named it Ernie. The detection of high-energy neutrinos like this confirms that nuclear fusion occurs in the core of the sun. Luminosity, total energy radiated by the sun, can be calculated from the fraction of the energy that reaches Earth. Total luminosity is about 3.86 times 10 to the 26 watts. This is equivalent of 10 billion 1 megaton nuclear bombs per second, compared to the largest bomb ever exploded, which was the 50 megaton Tsar bomb. The video link is actual footage of the Tsar bomb.